Hello everyone, I'm Charles de Carrario, and today I'm going to talk about a study we've conducted with Professor Fabrizio Scarpa from the Bristol Composite Institute and James Armstrong from the Medical School of the University of Bristol on the generalization of yield stress measurement in 3-point bending collapse test and its application to 3D-printed flax fiber reinforced hydrogel. So it's a study we've published in Biomedical Materials. In this study, we consider a material that we developed in a previous study, published in Soft Matter this time, and it's a flax fiber reinforced alginate-poloxamer hydrogel. Here's an example of a structure we produce with this material. In these structures, you have a first layer, which are concentric circles, and a second layer, which is sort of a flower shape structure. We were wondering, because the concentric circles have a distance between them, what is the distance at which we can print a second layer without the material collapsing in the distance of two successive circles in the first layer. And in order to understand this, the collapse test could be used, and that's what we did. But these structures, just to show you, is used as 4D printing before it actuates, basically. It deforms, it transforms when you change the environment of the structure. But then let's go back to collapse test. Collapse test consists basically in having a material, putting it between two different supports, like this old man handling this material. And if your material is soft enough, you obtain a curve, and from this curve, you can obtain properties of your material. In our case, our material is hyper-elastic and therefore fits the definition to be used in this material, because it could be 3D printed as well. This test happens with different pillars next to each other and with increasing distances, basically. And then we 3D print on top of these pillars. By 3D printing, you obtain a curve on your specimen, and from this curve, you can obtain different parameters. For instance, you can do collapse test, and from this collapse angle, sorry, theta R and theta L, and from this collapse angle, you can obtain the stresses inside your material. However, when we look at the literature, here's an example of 4 different papers that we've looked at. We were able to observe that the printing pressure seems to have an influence on the collapse test. So we measured ourselves the collapse test and the printing pressure compared to the printing pressure that these researchers used. And generally, when you increase the printing pressure, the collapse test increases as well. And so we were wondering what is the impact of the printing pressure on the different properties that we could measure in our material. So we took our material that I explained before, our 3D printer, our camera. We put our camera next in front of the 3D printer, 3D print on top of the pillar system that I've shown before, and measure different images during the test of the specimen. Here's an example of images that we obtained. The raw images that we converted into black and white images. Then we obtain the average position of the white pixel representing the average position of our specimen during the test. And you have to imagine that there is a pillar on each side of this image. This enables us to obtain the average position of our specimen, therefore sort of the shape of the specimen, and we could extract from this the angle, collapse angle for the specimen on the right and on the left. This was done for different time during the test. For instance, the first row represents just after printing, and the bottom row later, much later after printing. And you can see that the material evolves. It goes very much down at the beginning and then goes up in order to straighten with time, basically. So it's important to consider time in this test. One parameter that we were wondering about is symmetry. Basically, do we have symmetry between the two different sides of our specimen? In order to do this, we compared our collapse angle on the right and on the left of all our images. We compare for different printing pressure. Here is for 55 kilopascal, 60 kilopascal, and 70 kilopascal. And we were able to observe that for 50 kilopascal, there is no significant difference between the two parameters, between the two collapse angles. Same with 60 kilopascal. However, for 70 kilopascal, you have larger standard deviation, and there you have a significant difference between the two elements. In addition to this, when we did this test, so that's for stabilized values, when we, just after printing, if you take the first image after printing, for all the different pressure, you get asymmetric specimen. So in most contexts, you get asymmetric specimen. It's very important to consider the symmetry if you post-process that kind of material. But what should we do? Because most of the tests that have been done before is for symmetric material, or the unsymmetry of their material was not considered. So what we did is that we redefined a new set of equations for our specific material. So this is the image I've shown before. And the old equation use only one collapse angle. So it considers a symmetric between these two. Furthermore, it considers L, so as a distance between pillars. But if you look at what corresponds in the equation from which it is derived, it corresponds to the weight. The weight, when you have a little deformation, it makes sense to consider small L. However, for large deformation as we have in our specimen, it is important to consider the effective length of our specimen, which corresponds to the midpoint position of our white pixel that I've shown several slides ago, and the length of this curve, basically. And that's what we consider in our equations. So it gives a more complex system of equation. We consider the asymmetric deformation, and the distance between pillars is not anymore used in order to measure the weight, but it's the real length of the specimen which is measured to, which is used to measure the weight. And therefore, thanks to the new system of equations, we were able to obtain the yield stress of our specimen, which represents the stress at which the materials start deforming permanently from the different tests. We measured this yield stress for different time, and we were able to see that at the beginning there is some variation basically for all the different tests. So if to remind, this is 55 kilopascal printing pressure, 60 kilopascal printing pressure, 70 kilopascal printing pressure, and this is a bit specific. It's the same material but without reinforcement. So it's a different material basically. Very similar but different. And it was printed at 40 kilopascal. So this variation has to be taken into account. So what we did is considered something called the conversion time, which is the time at which the material converges towards within a 5% interval of its permanent value. And therefore, we were able to obtain this specific time and compare it for different printing pressure. And we were able to see that this conversion time is low for 55 kilopascal and then increasing for 60 and 70 kilopascal. And there's a significant difference between 50 and 60 and between 55 and 70 kilopascal, which shows that the material takes more time to obtain its permanent deformation for high pressure. And so if you consider that kind of test, you need to take into account the pressure that you use and understand how much time you need for your material to be able to obtain this final shape. So this is used for the material without reinforcement, no fiber. So it was printed at 40 kilopascal, and you see there is less data point. It's because at the gap that we've used for all these parameters, 10 millimeter, there was some failure in this one. And this failure enabled us to determine the strength of this material, which is very interesting for us because this strength could not be measured with standard test because it is too soft and could not even hold into a grip. And therefore, we compare the strength obtained between the old equations and the new equations, and we're able to see that there is a significant difference between the two strengths obtained. So it is interesting for us to use our new system of equation because we consider deeper, we have a more precise measurement with this new set of equations. Finally, one of the main reasons why we consider this study is to look at the printing pressure, printing and the pressure, and the importance it has on the results that we obtain. And the main result that we wanted to obtain was the yield stress. So this is the yield stress obtained for 55 kilopascal, 60 kilopascal, 70 kilopascal, and for without fiber. So you can see that there is significant difference between everything, basically. All the different printing pressure induce a significant difference in terms of yield stress, which is interesting, and that's why we added another material. is because it makes the comparison between materials difficult with this type of test. Because if you have one material and you want to compare to another one, this other material is going to have different viscosity, different properties, and therefore it's going to be printed at different printing pressure. And therefore, it is difficult to say we're going to compare this material to this one and obtain a yield stress if the printing pressure at which they are printing has an influence. However, our study of the printing pressure onto the different parameters obtained enable us a bit more to understand how material behaves with this printing pressure, and therefore make us a greater understanding of potential comparison that we would do with and without the fiber, for instance. So I'd like to thank you for listening to this presentation, and thank you for all the collaborators and funding bodies that helped me